Biofilm is a 3D network of bacteria enclosed in a self-generated extracellular polymeric matrix composed of proteins, lipids, polysaccharides, and nucleic acids. The presence of this matrix enables the biofilms to be resilient to adverse conditions, including the presence of antibiotics, high temperature, or changes in the pH. It is very challenging to form the opacity of the natural porous media of the biofilm. The shape, size, and connectivity between pores play a main role in defining the extent of a potential bacterial penetration. The difficulty of studying the bacterial accumulation in porous media is increased by the fact that the network of flow channels is generally moving. Different biofilm contains different combinations of bacteria. Due to this special behavior, a biofilm cannot be accurately identified with culture because the biofilm will not form in the culture dish the way it has inside the host.
The advent of 3D bioprinting bacterial biofilm plays a vital role in avoiding the crisis of post-antibiotic era. 3D bioprinting bacterial biofilm can be applied in antimicrobial resistance testing and screening of new drugs. For instance, this 3D bioprinting bacterial biofilm can act as an appropriate model for the antimicrobial susceptibility testing, as the bacterial biofilm can closely resemble in vivo biofilm formation, which is by mirroring in vivo bacterial growth and behaving more closely than conventional 2D models. These abilities increase the potential to investigate critical bacterial quorum sensing and to portray antimicrobial biofilm penetration. 3D bioprinting bacterial biofilm also increases the potential to produce biofilm constructs with pre-designed dimensions, with a high degree of control possible over biofilm thickness and dimensions. Thus, this advantage allows the study of drug penetration in 3D models, which was impossible to study in 2D models. A more instantaneous benefit could be testing the impact of drugs on biofilm infections for an individual patient.
Bacteria adheres to aqueous environment, forming gel-like substances which allow them to anchor to human or animal tissues. 3D bacterial biofilms need to be designed to fit closely to clinical biofilms in terms of their adhesion capabilities, mechanical properties, nutritional sources, and resistance to drug. It works better if the biofilm is thicker and in porous structure. Thicker biofilms have greater resistance toward antimicrobial drugs. Bacteria survive longer in thicker biofilm. Therefore, it would be ideal for research on drug development. Nutrient and oxygen diffusion and fluid transport can be facilitated if the structure is porous. Stable hydrogel system is crucial in forming 3D bacterial biofilm, allowing researchers to study the full cycle of biofilm development. Bacterial infection is harder to eradicate in a biofilm because the matrix is made of sugar molecules, forming a physical and chemical barrier. Researchers can study on how to break through the barrier more effectively so that it can facilitate drug diffusion into the target site, thus preventing secondary microbial infections and health complications.